Hello there, and welcome to the Science for Sleep channel. I'm so glad you found your way here tonight. Maybe you've had a long day, or maybe you're simply the kind of person who likes drifting off to something vast and quiet rather than counting sheep. Either way, this journey is for you. You've got nothing to do now but rest. Let your mind soften, your breathing slow, and your body grow light as if gravity itself has loosened its hold. Because tonight, we aren't simply looking at stars. We're floating through the Milky Way, our home galaxy, a spiral of light turning slowly through the darkness of space. 200 billion stars or more, all drifting in their ancient orbits, all part of one vast, patient structure that has been turning for over 13 billion years. Some of those stars are older than the galaxy itself. Others were born just yesterday, in cosmic terms. And all of them, every single one, moves through space together, held by invisible threads of gravity, weaving patterns we can barely imagine. Tonight, we'll explore this galaxy gently, one quiet fact at a time. Some of what you hear may surprise you, or spark a gentle curiosity as you drift towards sleep. But there's no need to hold on to anything. Just let it wash over you soft and slow, like waves on a distant shore. And before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. The Milky Way has already collided with other galaxies, not once but many times across its long history. Smaller galaxies wandered too close, drawn in by gravity's patient pull, and the Milky Way absorbed them. Their stars scattered and mixed with ours, their patterns erased, their identities dissolved into the larger whole. Around 8 to 10 billion years ago, a dwarf galaxy smashed into the Milky Way in what astronomers now call the Gaia sausage collision. The impact was dramatic, head-on, and it reshaped our galaxy's structure. The dwarf galaxy did not survive. It fell apart, its stars flung onto radial orbits that still carry them through the Milky Way's heart today, like needles threading through fabric. And there are stars in our galaxy older than the galaxy itself. This seems impossible at first, doesn't it? But some ancient stars formed before the Milky Way took its current shape, back when the universe was still very young. These halo stars orbit in the outer reaches, relics from an earlier era, witnesses to the galaxy's slow assembly. They are metal poor, formed from nearly pristine hydrogen and helium before generations of supernovae enriched the cosmos with heavier elements. They remind us that galaxies are not born complete. They grow, they change, they gather pieces from the universe around them. At the very heart of the Milky Way sits a supermassive black hole. It has a name, Sagittarius O, and it weighs more than 4 million times the mass of our Sun. Across space, it spans about 51 million kilometers, smaller than the distance from Earth to the Sun, yet containing all that mass compressed into an impossibly small region. For years, astronomers could not see it directly, hidden behind clouds of dust and gas, but they watched stars orbiting something invisible, moving at extraordinary speeds. Some of those stars complete an orbit in just 16 years, racing around the black hole in tight ellipses that reveal its immense gravitational pull. In about 4 billion years, perhaps a bit more, the Milky Way may collide with Andromeda, our neighboring galaxy. For a long time, astronomers believed this collision was certain, inevitable, a cosmic appointment written in the trajectories of galaxies. But recent studies suggest the future is less determined than we thought. New calculations show only about a 50% chance of a merger within the next 10 billion years. If the galaxies do collide, it will happen slowly, over millions of years, their spiral arms interpenetrating, their stars passing like ghosts through vast empty spaces. The night sky will change. Andromeda will grow larger, brighter, until the two galaxies blend into one. The Milky Way is not flat, not perfectly round, not elegantly symmetrical. It is warped and twisted, bent out of shape by gravitational interactions with neighboring galaxies. The disk ripples and curves like a record someone sat on. These wrinkles were likely caused by a dwarf galaxy colliding with the Milky Way around 2.7 billion years ago, relatively recently in cosmic terms. The collision sent waves through the galactic disk, distortions that still persist, visible to spacecraft like Gaia that map the positions and motions of millions of stars. Most of the galaxy's mass is invisible. We cannot see it, cannot touch it, cannot detect it directly. It is called dark matter, and it makes up about 90% of the Milky Way's total mass. Only a small fraction comes from stars, planets, gas, and dust, the luminous matter we can observe. Dark matter shapes the galaxy's structure, provides the gravitational scaffolding that holds everything together, determines how fast stars orbit. Without it, the galaxy would fly apart. But what dark matter actually is remains one of the deepest mysteries in science. The Milky Way recycles its dead stars into new ones. When massive stars exhaust their fuel, they explode as supernovae, blasting their enriched contents back into space. This material, seeded with carbon, oxygen, iron, and heavier elements forged in stellar cores, mingles with clouds of hydrogen and helium. Over time, gravity pulls these clouds together, and they collapse, igniting nuclear fusion, birthing new generations of stars. Our sun is one of these later generation stars. The atoms in your body, the oxygen you breathe, the calcium in your bones, were all created inside stars that died long before the solar system formed. The Milky Way has cannibalized dozens of smaller galaxies over its history. Their remnants still orbit through the halo, streams of stars that trace their doomed trajectories. Astronomers call these stellar streams, and they are fossils, archaeological evidence of ancient collisions and mergers. Each stream tells a story of a smaller galaxy that wandered too close, torn apart by tidal forces, its stars strewn across space. The Milky Way is not a static object. It is a dynamic system, still growing, still consuming, still changing. The galaxy rotates, but not like a solid disk. Stars closer to the center move faster than stars farther out, and yet the outer stars also move faster than expected based on visible matter alone. This is differential rotation, a pattern shaped by the distribution of mass, both visible and dark. The spiral arms themselves are not permanent structures. They are density waves, regions where stars and gas temporarily pile up as they orbit, creating the appearance of spiral patterns. Stars drift into the arms, linger for a while, then move on, like cars passing through a slow patch of traffic. And massive stellar explosions, supernovae, have sculpted the galaxy's structure over billions of years. They blast bubbles and cavities into the interstellar medium, clear out regions hundreds of light years wide, trigger the collapse of nearby clouds to form new stars. The galaxy is not smooth or uniform. It is textured, shaped by violence and creation in equal measure, a vast ecosystem where stars are born, live, and die, their endings seeding the beginnings of others. These massive stellar explosions, these supernovae, have done more than carve bubbles in space. They have shaped the entire chemical evolution of the galaxy. Every supernova blasts newly forged elements into the interstellar medium, enriching clouds that will someday collapse into new stars and planets. The first generation of stars contained almost no heavy elements, just hydrogen and helium from the Big Bang. But each generation that followed inherited a richer mix, seeded by the deaths of stars that came before. The Milky Way has been enriched slowly, patiently, over billions of years. The galaxy is almost as old as the universe itself. At 13.6 billion years old, the Milky Way formed just 100 million years after the Big Bang, when the cosmos was still young and hot. Some of its oldest stars, found in globular clusters, are nearly that ancient, relics from the galaxy's earliest days. These globular clusters orbit the galaxy like satellites, spherical collections of hundreds of thousands of stars, all born at roughly the same time from the same cloud. They are fossils, preserved samples of the conditions that existed when the galaxy was assembling itself. A river of hydrogen gas flows into the Milky Way. It is called the Magellanic Stream, and it stretches across 600,000 light-years of space, trailing. Behind the large and small Magellanic Clouds, two small galaxies that orbit the Milky Way. The stream was discovered in 1972, a ribbon of neutral hydrogen arcing across the southern sky. It was formed by tidal forces, the Milky Way's gravity pulling gas from its companion galaxies as they orbit. This gas will eventually fall into the Milky Way, feeding future generations of star formation. The galaxy's spiral arms are not permanent structures. This is one of the most surprising facts about spiral galaxies. The arms are not solid objects, not fixed formations of stars moving together. They are density waves, regions where stars and gas temporarily pile up as they orbit the galactic center. Think of them as traffic jams in space. Stars move into the arms, slow down slightly, pile up, then move on. The density wave itself rotates more slowly than the stars, creating the illusion of stable spiral patterns. But the stars passing through are always changing. Thousands of globular clusters orbit the Milky Way. The current count stands at around 160 known clusters, but astronomers believe more remain hidden, obscured by dust or lurking in the far reaches of the galactic halo. Some globular clusters contain millions of stars packed into spheres just a few dozen light-years across. They are among the oldest objects in the galaxy, some dating back over 13 billion years. Many have retrograde orbits, meaning they revolve around the galaxy in the opposite direction from the disk's rotation, evidence that they formed separately and were captured later. The galactic center glows with infrared light. Dust blocks visible light from reaching us, but infrared radiation passes through, revealing a crowded, violent region packed with massive stars. The center is a place of extremes where stars orbit the supermassive black hole at incredible speeds, where gas clouds heat to millions of degrees, where stellar winds and radiation pressure shape the environment on scales both vast and small. It reminds us that the galaxy is not uniform, not everywhere calm and quiet like the region where we live. Stars are born in the spiral arms, cold molecular clouds composed mostly of hydrogen molecules, drift through space until they encounter a density wave. The compression triggers collapse. Gravity pulls the cloud inward, the center heats up, and eventually nuclear fusion ignites. A new star is born. Some of these stars are massive, burning bright and blue, illuminating the spiral arms where they form. Others are smaller, redder, longer-lived. This tells us that star formation is ongoing, that the galaxy is still actively creating new stars from the raw material of old ones. The Milky Way has a thick disk and a thin disk. Two distinct populations of stars occupy different vertical heights above the galactic plane. The thin disk contains younger stars, stars like the Sun, stars born from gas that has settled into a relatively flat configuration. The thick disk contains older stars with different chemical compositions, different velocities, different orbits. They were likely formed during the galaxy's more turbulent early history, when mergers and interactions stirred the disk and puffed it up. Cosmic rays stream through the galaxy at nearly the speed of light. These are not rays of light, but high-energy particles, mostly protons, accelerated to incredible energies by supernova shock waves and other violent events. They permeate the interstellar medium, ionizing atoms, driving chemical reactions, influencing the dynamics of molecular clouds. Some cosmic rays reach Earth, raining down through the atmosphere, occasionally detected by instruments on the ground or in space. They remind us that space is not empty, but filled with invisible activity. The galaxy's bar drives gas toward the center. The Milky Way is a barred spiral galaxy with a central bar-shaped structure made of stars and gas. This bar is not static, it rotates, and as it does, it exerts gravitational torques on the surrounding material, funneling gas inward along its edges. This feeds star formation in the central regions and may also feed the supermassive black hole at the very center. The bar formed relatively recently in the galaxy's history, within the last few billion years, and it has reshaped the inner disk. Rogue planets wander the galaxy without stars. Billions of them, perhaps trillions, drift through interstellar space, orphaned worlds ejected from their birth systems by gravitational interactions. Some estimates suggest rogue planets outnumber stars in the Milky Way by 20 to 1. They were born around stars, formed in protoplanetary disks, just like Earth and Jupiter, but something went wrong. A close encounter with another planet or a passing star kicked them loose. Now they travel alone through the darkness, unlit, unwarmed, moving through the galaxy on their own silent trajectories. The Sun takes 230 million years to orbit the galactic center. This is called a cosmic year, the time required for our solar system to complete one full revolution around the Milky Way. The Sun moves at about 220 kilometers per second through space, carrying all the planets with it. Since the Sun formed about 4.6 billion years ago, it has completed roughly 20 orbits around the galaxy. Each time it circles, it passes through different regions, sometimes through spiral arms, sometimes through quieter spaces between them. Magnetic fields thread through the entire galaxy. Invisible lines of magnetic force permeate the interstellar medium, shaped by rotation, by stellar winds, by supernova explosions. These fields are weak, thousands of times weaker than Earth's magnetic field, but they stretch across vast distances. They guide the motion of charged particles, cosmic rays that stream through space. They influence the collapse of molecular clouds, the formation of stars. Some regions have stronger fields, others weaker, complex tapestry woven through the galaxy's structure. The Milky Way is surrounded by a hot, gaseous halo. This corona of ionized gas extends far beyond the visible disk, heated to temperatures of hundreds of thousands or even millions of degrees. The gas was blasted from the galactic plane by supernova explosions, fountains of hot material ejected into the halo. As the gas cools, it falls back into the disk, enriched with heavy elements forged in stellar cores, ready to be recycled into new generations of stars. This cycle has repeated countless times over the galaxy's history. Star clusters are slowly dissolving. Long ago, they formed from single clouds of gas, hundreds or thousands of stars born together, gravitationally bound. Over time, they lose members to the galactic tide. Close encounters between stars transfer energy, kicking some stars to higher speeds. Eventually, those stars escape, drifting away into the galaxy. Even now, ancient clusters continue to evaporate, their stars scattering across space, their identities fading into the larger population. The galaxy contains between 100 billion and 400 billion stars. The exact count remains uncertain because many stars are too faint or too obscured to detect. Some are small red dwarfs, barely massive enough to sustain fusion, glowing dimly for trillions of years. Others are massive blue giants, burning bright and fast, living only a few million years before exploding. This reminds us that the galaxy is not uniform, not made of identical pieces, but a diverse ecosystem of stellar life. The Milky Way spans about 100,000 light years across. Light, traveling at 300,000 kilometers per second, would take 100,000 years to cross from one edge of the galactic disk to the other. Yet even this vast structure is not isolated. It belongs to a larger cosmic web, connected by gravity to other galaxies, part of structures that span millions and tens of millions of light years. This tells us that scale in the universe is almost beyond comprehension. Our solar system resides in a minor spiral arm. We orbit in the Orion Arm, sometimes called the Orion Spur, a small branch between two major spiral arms, the Perseus Arm and the Sagittarius Arm. We are not at the center, not at the edge, but somewhere in between, about 26,000 light years from the galactic center. This location may be significant, too close to the center, and radiation from the supermassive black hole and frequent supernova explosions might sterilize planets. Too far out, and there might not be enough heavy elements to form rocky worlds. The galactic disk is incredibly thin relative to its width. If the Milky Way were scaled down to the size of a pancake, it would be thinner than a sheet of paper. The disk is only about 1,000 light years thick, but 100,000 light years wide. Stars orbit in roughly the same plane, held there by the combined gravitational pull of all the mass in the disk. Some stars have orbits tilted out of the plane, but most stay close, contributing to the disk's flatness. Interstellar dust obscures much of the galaxy. Tiny particles, smaller than grains of smoke, scatter and absorb starlight, especially blue light. This makes distant stars appear redder and dimmer than they actually are. It also hides the galactic center from view in visible wavelengths. To see through the dust, astronomers use infrared and radio telescopes, which detect longer wavelengths that pass through the dust relatively unimpeded. And all of this exists together, moving, turning, folding through time. The galaxy's oldest stars contain almost no heavy elements. Long ago, before supernovae enriched the cosmos with metals, the first generation of stars formed from nearly pristine hydrogen and helium. Over time, these population 3 stars exploded, seeding space with carbon, oxygen, iron, and other elements forged in their cores. Even now, some ancient halo stars remain, relics from that early era, their compositions revealing the conditions of the infant universe. This reminds us that stars are not all alike, not all born from the same mixture of elements. Gas clouds in the galaxy can be colder than outer space. Some molecular clouds reach temperatures just a few degrees above absolute zero, colder than the cosmic microwave background radiation that fills the universe. These clouds are shielded from starlight by dust, insulated from the heat of nearby stars. In their frozen depths, Molecules form, hydrogen atoms pair up, and gravity begins the slow work of pulling material together. Over millions of years, these cold clouds will collapse and new stars will ignite. The Milky Way belongs to a galaxy group called the Local Group. About 80 galaxies share this cosmic neighborhood, bound together by gravity, moving through space as a collection. Some members are large spiral galaxies like Andromeda and the Milky Way. Others are small dwarf galaxies, irregulars, ellipticals. The entire group spans roughly 10 million light-years, with its center somewhere between the two largest members. It tells us that galaxies are not isolated islands, but members of communities shaped by their mutual attraction. Stellar winds from massive stars carve bubbles in space. Hot gas blown from the surfaces of dying stars clears cavities hundreds of light-years wide, sweeping up material, compressing it into shells. Some of these bubbles overlap, creating networks of tunnels and chambers carved through the interstellar medium. The galaxy is not smooth or uniform, but textured, shaped by the lives and deaths of its stars, by forces both gentle and violent, acting over immense stretches of time. The galaxy's halo extends far beyond the visible disk. This spherical region surrounds the flat disk, containing old stars, globular clusters, and vast amounts of dark matter. Some stars in the halo orbit in directions opposite to the disk's rotation, evidence they formed separately or were captured from smaller galaxies. Others move on highly elliptical paths, plunging through the disk and back out again. It reminds us that the galaxy has multiple components, each with its own history, its own story to tell. Binary star systems are common throughout the galaxy. More than half of all stars have at least one companion star, bound together by gravity, orbiting their common center of mass. Some binaries are close, their surfaces nearly touching, exchanging material in complex dances. Others are wide, separated by thousands of astronomical units, barely influencing each other. This tells us that stellar formation often produces not single stars, but pairs, triplets, even larger groups born from the same collapsing cloud. The Milky Way rotates once every 250 million years at our distance. Long ago, when dinosaurs walked on Earth, the Sun was on the opposite side of the galaxy. Over time, it has drifted through different regions, encountered different stellar populations, passed through spiral arms and quiet spaces. Even now, it continues its patient orbit, carrying the solar system through the vast structure of the galaxy, a journey that will continue for billions of years to come. Nebulae glow with the light of nearby stars. Ultraviolet radiation from hot, young stars ionizes the surrounding gas, stripping electrons from atoms. When electrons recombine with atoms, they emit light at specific wavelengths, creating the colorful glows astronomers photograph. Some nebulae shine red from hydrogen, others green from oxygen, still others blue from scattered starlight. This reminds us that space is not dark everywhere, but lit in places by the energy of stars. The galaxy's central bulge formed early in its history. This dense spheroid of older stars predates much of the disk, assembled from the merger of smaller protogalactic fragments billions of years ago. Stars in the bulge are older on average, more metal-poor, moving on more random orbits than stars in the disk. The bulge tells a story of the galaxy's violent youth when it was still gathering mass, still taking shape from the chaos of the early universe. Dust lanes trace the spiral arms, dark ribbons marking where gas has piled up along the density waves. These lanes are not empty but filled with cold molecular clouds, regions where stars will someday form. Long ago, our sun was born in one of these dust lanes. Over time, it drifted away from its birthplace. Even now, other stars are forming in these same regions, continuing the cycle that has played out for billions of years. And through all of this, the galaxy continues its ancient turning, patient and endless. The Milky Way is moving through space at 600 kilometers per second. Long ago, when the universe was younger, our galaxy began its journey toward the Virgo cluster, pulled by the gravity of a vast concentration of mass astronomers call the Great Attractor. Over time, this motion has carried the galaxy millions of light years through space, though from our perspective inside it, we notice nothing. Even now, the galaxy continues to move, drawn by invisible forces, drifting through the expanding cosmos at speeds that dwarf anything we experience in our daily lives. This reminds us that nothing in the universe is truly at rest. Open star clusters are younger than globular clusters. Some open clusters contain stars that formed just a few million years ago, still hot and blue, still surrounded by remnants of the gas clouds from which they were born. Others contain older stars, though none approach the ancient ages of globular cluster members. These clusters are looser, less tightly bound, spread across tens of light years rather than compact spheres. Over time, they will dissolve, their stars drifting apart, scattered by gravitational encounters with other objects passing through the galaxy. The galactic plane is tilted relative to the solar system. Long ago, the solar system's formation disk settled into a particular orientation. Over time, as the sun orbited the galaxy, this orientation remained fixed relative to distant stars. Even now, we view the Milky Way's disk edge on from Earth, a luminous band stretching across the night sky. This tells us that our perspective shapes what we see, that the galaxy appears different depending on where we stand and how we look. Gamma-ray bubbles extend above and below the galactic center. The Fermi bubbles stretch 25,000 light years, enormous lobes of hot plasma glowing with high-energy radiation. Some astronomers believe they were created by ancient activity from the supermassive black hole, a period when it consumed matter more violently and blasted jets of energy into space. Others suggest concentrated star formation near the center could have driven powerful winds that carved these structures. The bubbles are relatively young, perhaps only a few million years old, evidence of dramatic events in the galaxy's recent past. Most stars in the galaxy are smaller than the Sun. Red dwarf stars with masses between 8% and 60% of the Sun's mass vastly outnumber larger, brighter stars. Some estimates suggest red dwarfs make up about 73% of all stars in the Milky Way. Others burn dimly for trillions of years, far longer than the current age of the universe, conserving their fuel through slow, patient fusion. This reminds us that the galaxy is populated mostly by stars we cannot see with the naked eye, faint embers burning in the darkness. The galaxy's magnetic field follows spiral patterns. Long ago, the field was weaker, less organized. Over time, rotation and turbulence wound the field lines into spiral shapes that mirror the density waves of the spiral arms. Even now, cosmic rays stream along these field lines, charged particles guided by invisible magnetic forces. Field lines wind through interstellar space, threading between stars, connecting regions separated by thousands of light years. It tells us that the galaxy is not just matter moving through empty space, but matter embedded in fields that shape its behavior. Supernova remnants enrich the interstellar medium. Some remnants are young, still expanding rapidly. their shock waves glowing brightly in X-rays and radio waves. Others are old, faded, dispersed into the surrounding gas until they become indistinguishable from the general background. Each explosion adds newly forged elements to the galaxy, carbon and oxygen and iron and dozens of others. Over time, these elements mix into molecular clouds, ready to be incorporated into the next generation of stars and planets. The Milky Way has satellite galaxies orbiting it. Some are visible to the naked eye, like the large and small Magellanic Clouds, irregular dwarf galaxies that orbit our galaxy from the southern hemisphere. Others are so faint they were discovered only recently, dwarf spheroidals containing just a few thousand stars scattered across thousands of light years. Long ago, these satellites were independent systems. Over time, the Milky Way's gravity captured them. Even now, tidal forces slowly strip stars and gas from these companions, feeding our galaxy's continued growth. Pulsars sweep beams of radiation across the galaxy. These rapidly spinning neutron stars emit lighthouse-like pulses as their magnetic poles sweep past our line of sight. Some pulsars spin hundreds of times per second, remnants of massive stars compressed to spheres just 20 kilometers across. Others spin more slowly, their rotation gradually decelerating as they lose energy through radiation. Long ago, each pulsar was a massive star. Over time, it exhausted its fuel, exploded, and collapsed. Even now, thousands of pulsars shine throughout the galaxy, cosmic beacons marking the graves of dead stars. The Sun orbits at a distance of about 26,000 light-years from the center. Long ago, it formed in a molecular cloud somewhere in the galactic disk, perhaps closer to the center than it is now, perhaps farther out. Over time, gravitational interactions with spiral arms and giant molecular clouds have nudged its orbit, causing it to migrate slowly. Even now, it continues its patient journey around the galaxy, a journey that will last for billions of years, through regions calm and turbulent, empty and crowded. And so the galaxy turns, quietly, patiently, as it has for billions of years and will for billions more. Stars form from collapsing clouds of gas and dust. Long ago, before any particular star existed, there was only a cold, molecular cloud drifting through the galaxy, composed mostly of hydrogen molecules and microscopic dust grains. Over time, gravity pulled material together, slowly at first, then faster as the density increased. Even now, in countless regions throughout the galaxy, the same process continues. Clouds collapsing under their own weight until nuclear fusion ignites at their cores and new stars begin to shine. This reminds us that star formation is not an event from the distant past, but an ongoing process that has continued for billions of years. The galaxy continuously recycles matter. Some elements are locked inside stars, fused in stellar cores, or bound in planetary bodies. Others drift through interstellar space as gas and dust, waiting to be gathered into new clouds. Long ago, these same atoms existed in different forms, perhaps in ancient stars that exploded long before the sun formed. Over time, they have cycled through multiple generations, each passage adding more heavy elements to the mix. Even now, the carbon in our bodies, the oxygen we breathe, moves through this cosmic cycle, borrowed temporarily from the galaxy, destined to return when the sun dies, billions of years from now. Light from distant stars takes thousands of years to reach us. Long ago, when that light began its journey, the star might have been in a different position. The galaxy might have looked subtly different. Over time, the photons traveled through space, passing through dust clouds, gravitational fields, empty voids. Even now, we see the galaxy not as it is in this moment, but as it was, a mosaic of different times depending on the distance to each star we observe. This tells us that observing the universe is also observing the past. The spiral arms rotate more slowly than the stars. Long ago, astronomers wondered why spiral patterns persist if stars move faster than the arms themselves. Over time, they realized that the arms are not made of fixed groups of stars, but are density waves, patterns where stars temporarily slow down and pile up as they pass through. Even now, stars drift into the arms, linger for a time, then move on, like vehicles passing through a region of heavy traffic. Some stars are in the arms. Others have already passed through and moved into the quieter spaces between. This reminds us that appearances can be deceiving, that structure does not always mean permanence. Different regions of the galaxy have different metallicities. Long ago, when the galaxy was young, stars everywhere contained very few heavy elements, formed from nearly pristine hydrogen and helium. Over time, supernovae enriched the inner regions faster than the outer regions, creating a gradient that stretches from the metal-rich center to the metal-poor edge. Even now, stars forming near the galactic center inherit more iron, carbon, and oxygen than stars forming in the outer disk. Some regions are enriched quickly, others are enriched more slowly. This tells us that the galaxy is not chemically uniform, but shaped by the history of star formation and element production. Gas in the galaxy is mostly hydrogen and helium. Long ago, these were the only elements present in significant quantities, created during the Big Bang, when the universe was just minutes old. Over time, stars have forged heavier elements in their cores, but hydrogen and helium still dominate, making up about 98% of all baryonic matter. Even now, molecular clouds that will someday collapse to form new stars consist primarily of these two simplest elements. Some clouds contain traces of carbon, oxygen, nitrogen, and heavier elements. Others contain even less, preserving compositions closer to primordial conditions. The galactic disk grows thicker with age. Long ago, the disk was thinner, stars moving in more circular orbits confined closer to the galactic plane. Over time, gravitational interactions with spiral arms, molecular clouds, and other structures gradually increase the vertical velocities of stars, puffing up the disk. Even now, this process continues, older stars drifting to greater heights above and below the plane than younger stars. Some stars remain close to the plane throughout their lives. Others wander far from where they formed, their orbits tilted by encounters with massive objects passing nearby. Some stars escape the galaxy entirely. Long ago, gravitational interactions near the galactic center or in dense star clusters occasionally accelerated stars to speeds high enough to overcome the galaxy's gravity. Over time, these high-velocity stars have traveled thousands of light years beyond the disk, some leaving the Milky Way altogether. Even now, a small population of hypervelocity stars race through intergalactic space, unbound, destined never to return. Others move more slowly, but still fast enough to reach the distant halo. This reminds us that the galaxy's gravitational hold, while strong, is not absolute. The black hole at the center is relatively quiet now. Long ago, perhaps millions or billions of years in the past, Sagittarius AA may have been more active, consuming matter more rapidly, blazing with radiation. Over time, it settled into a quieter state, accreting gas slowly, producing only occasional flares when small amounts of material fall inward. Even now, astronomers watch for these flares, brief brightenings that reveal the black hole's presence. Some observations show activity, others show calm. This tells us that supermassive black holes are not always voracious devourers, but can remain dormant for long periods, patient and dark at the galaxy's heart. Dust grains are smaller than particles of smoke. Long ago, these microscopic particles formed in the atmospheres of dying stars, condensing from hot gases as they cooled. Over time, they drifted into interstellar space, mixed with gas, coated with ices. Even now, they fill the galaxy, blocking and scattering starlight, providing surfaces where molecules can form. Some grains are silicates, rock-like minerals. Others are carbonaceous, soot-like materials. And the galaxy continues, turning, folding, moving through space and time, patient and endless. The Milky Way's mass is concentrated toward the center. Long ago, when the galaxy was forming, material fell inward under gravity, settling into a dense central bulge surrounded by a flatter disk. Over time, this distribution has remained relatively stable, though interactions and mergers have added complexity. Even now, the inner few thousand light years contain a disproportionate fraction of the galaxy's total mass, both invisible stars and invisible dark matter. Some regions hold more mass than others. Others hold less. This reminds us that the galaxy is not uniform in its structure, but shaped by the forces that assembled it billions of years ago. Stellar populations reveal the galaxy's history. Long ago, the first generation of stars formed from pristine gas, containing almost no heavy elements. Over time, these population stars aged, while new population stars formed from enriched material. Even now, we can distinguish these populations by their chemical compositions, their locations, and their orbital motions. Some stars belong to population 1, found in the disk, following circular orbits. Others belong to population 2, found in the halo, following eccentric paths that carry them far above and below the galactic plane. This tells us that studying stars allows us to read the history written in the galaxy's structure. Gas flows both inward and outward in the galaxy. Long ago, material fell into the galaxy from intergalactic space, feeding the disk with fresh hydrogen. Over time, some of this gas has cycled through stars, been ejected by supernovae, and fallen back toward the plane. Even now, fountains of hot gas rise from the disk into the halo, cool, and descend again. Some gas moves inward, drawn by the central bar and spiral density waves. Others moves outward, pushed by stellar winds and supernova explosions. This reminds us that the galaxy is not static, but filled with flows and circulations on vast scales. The Sun has migrated from where it formed. Long ago, approximately 4.5 billion years ago, the Sun was born in a molecular cloud somewhere in the galactic disk, possibly at a different distance from the center than it occupies now. Over time, gravitational interactions with spiral arms and the central bar have nudged its orbit, causing it to drift radially through the disk. Even now, studies suggest the Sun may have migrated from the outer regions of the disk inward to its current position, though the exact amount of migration remains uncertain. Some stars migrate significantly during their lifetimes. Others remain closer to their birth locations. This tells us that stellar orbits are not fixed, but evolve gradually over billions of years. Cold, dark matter shapes the galaxy's structure. Long ago, Before visible stars formed, dark matter had already collapsed into halos, providing the gravitational scaffolding that would guide the assembly of galaxies. Over time, normal matter fell into these dark matter wells, settling into disks where stars could form. Even now, dark matter dominates the mass distribution, extending far beyond the visible disk into a vast spherical halo. Some dark matter exists in the inner galaxy. Others exists in the outer regions. This reminds us that most of the galaxy's mass is invisible, detectable only through its gravitational effects. The galaxy contains vast amounts of empty space. Long ago, when stars formed, they were separated by light years of near vacuum, with only occasional atoms drifting between them. Over time, the average density has remained extraordinarily low, far emptier than the best vacuum we can create on Earth. Even now, interstellar space is mostly emptiness, punctuated by occasional clouds of gas and dust. Some regions contain more matter than others. Others contain almost nothing. This tells us that despite containing hundreds of billions of stars, the galaxy is overwhelmingly composed of empty space. Molecular hydrogen is difficult to detect directly. Long ago, astronomers realized that hydrogen molecules do not emit radiation easily at the cold temperatures found in molecular clouds. Over time, they learned to use tracer molecules like carbon monoxide, which emit more readily and correlate with hydrogen density. Even now, most observations of star-forming regions rely on these tracers rather than detecting hydrogen molecules themselves. Some clouds are detected through carbon monoxide emission, others are detected through dust absorption. This reminds us that observing the universe often requires indirect methods, measuring proxies rather than the objects of interest directly. The Milky Way's rotation curve reveals dark matter. Long ago, astronomers measured the velocities of stars and gas clouds at different distances from the galactic center. Over time, they discovered that these rotation curves remain flat or even rise slightly at large distances, rather than declining as expected from visible matter alone. Even now, this remains one of the strongest pieces of evidence for dark matter's existence. Some regions rotate faster than visible matter predicts. Others rotate at speeds that require invisible mass. This tells us that our understanding of the galaxy's mass distribution depends critically on observations of how objects move through space. Star formation rates have declined over time. Long ago, when the galaxy was young and gas-rich, stars formed more rapidly than they do today. Over time, as gas was consumed and some was ejected from the galaxy, the rate of new star formation gradually decreased. Even now, the Milky Way continues to form stars, but at a slower pace than in its youth. Some epochs produced many stars quickly. Others produced fewer stars more slowly. This reminds us that galaxies age, that they change over cosmic time scales, evolving from vigorous youth to quieter maturity. The galactic center hosts unusual stellar orbits. Long ago, these stars formed in the crowded environment near the supermassive black hole, or perhaps migrated inward from greater distances. Over time, gravitational interactions with the black hole and with each other have shaped their orbits into highly elliptical paths. Even now, some of these stars pass within a few light days of the black hole's event horizon, traveling at significant fractions of the speed of light. Some orbits are elongated, carrying stars close to the black hole and far away in long ellipses. Others are more circular, though still influenced by the black hole's immense gravity, and the galaxy turns quietly, patiently, folding through time. Interstellar clouds shield forming stars from radiation. Long ago, before a star ignited nuclear fusion at its core, it existed as a dense knot of gas buried deep within a molecular cloud, surrounded by layers of dust and molecules that blocked external radiation. Over time, as the protostar grew and heated, it began to illuminate its surroundings from within, but the outer layers continued to protect it from the harsh, ultraviolet light of nearby massive stars. Even now, throughout the galaxy, countless protostars remain cocooned in these dense envelopes, invisible to optical telescopes but glowing in infrared wavelengths. Some clouds provide thick shielding that lasts for millions of years. Others provide thinner protection that erodes more quickly. This reminds us that star formation is a process that unfolds gradually, hidden from direct view in the quiet darkness of collapsing clouds. The galaxy's age is determined from its oldest stars. Long ago, astronomers realized that measuring the ages of globular cluster stars would provide a minimum age for the Milky Way itself, since these clusters formed early in the galaxy's history. Over time, improved observations and models of stellar evolution have refined these age estimates, converging on values around 13.6 billion years for the oldest clusters. Even now, new measurements continue to test and refine this ancient age, using techniques that compare observed stellar properties with theoretical predictions. Some stars appear older. Others appear slightly younger. This tells us that the galaxy assembled over an extended period, not in a single instant, but through a gradual process of formation and growth. Chemical abundances vary across the galactic disk. Long ago, when the first stars formed near what would become the galactic center, they quickly enriched that region with heavy elements from their supernova explosions. Over time, star formations spread outward, creating a gradient where metallicity decreases with increasing distance from the center. Even now, stars forming in the inner disk inherit more iron, oxygen, and other heavy elements than stars forming in the outer regions. Some regions contain metal-rich stars. Others contain metal-poor stars. This reminds us that the galaxy's chemical composition is not uniform, but reflects the history of where and when stars formed and died. The Milky Way is part of the Virgo supercluster. Long ago, gravity began gathering galaxies into larger and larger structures, forming groups, then clusters, then superclusters that span hundreds of millions of light years. Over time, the local group, containing the Milky Way and Andromeda, has remained an outlying member of the Virgo supercluster, centered on the Virgo cluster, about 54 million light-years away. Even now, the gravity of this massive structure influences the motion of the Milky Way, pulling it toward the cluster center. Some galaxies orbit close to the supercluster's heart. Others orbit far from the center, like the Milky Way. This tells us that our galaxy belongs to a vast cosmic web, connected by gravity to structures that dwarf even the largest individual galaxies. Stellar winds gradually disperse gas clouds. Long ago, massive stars began their lives by forming in dense molecular clouds, but as they ignited and matured, their intense radiation and powerful winds started to push away the surrounding material. Over time, these winds carved bubbles and cavities, clearing space around the stars, fragmenting the clouds into smaller pieces. Even now, stellar winds continue this work throughout the galaxy, dispersing gas, reducing the mass available for future star formation. Some winds are gentle, from low-mass stars like the Sun. Others are violent, from massive hot stars that blow away hundreds of solar masses of material over their brief lifetimes. This reminds us that stars both form from gas and also destroy the clouds that birth them. Stars move in elliptical orbits around the galactic center. Long ago, when each star formed, gravitational interactions with nearby gas clouds, other stars, and spiral density waves perturbed its orbit, changing its shape from circular to elliptical. Over time, these perturbations accumulated, with some stars developing highly elongated orbits, while others remained nearly circular. Even now, the orbits continue to evolve slowly, shaped by every gravitational encounter, every passage through a spiral arm. Some stars follow elongated ellipses that carry them far from the galactic plane. Others follow flatter orbits that keep them close to where they formed. This tells us that stellar orbits are not fixed paths, but dynamic trajectories shaped by the complex gravitational environment of the galaxy. The galaxy's appearance changes with wavelength. Long ago, astronomers could observe only invisible light, seeing a narrow slice of the electromagnetic spectrum. Over time, telescopes were built to observe infrared, radio, ultraviolet, X-ray, and gamma-ray light, each revealing different components and structures. Even now, observations at different wavelengths show dramatically different versions of the same galaxy. Some wavelengths reveal hot gas and young stars. Others reveal cold dust and molecular clouds. This reminds us that no single view captures the full complexity of the galaxy. That understanding requires observations across the entire spectrum. Dust extinction makes distant stars appear redder. Long ago, light from distant stars began its journey through the galaxy, passing through regions filled with microscopic dust grains. Over time, these grains scattered and absorbed the light, with blue wavelengths affected more strongly than red wavelengths. Even now, when we observe stars on the far side of the galaxy, we see them not in their true colors, but reddened and dimmed by intervening dust. Some stars appear much redder than they truly are. Others are less affected, located along clearer lines of sight. This tells us that observing the galaxy requires correcting for the effects of dust that lies between us and the objects we study. The Milky Way is gravitationally bound to its neighbors. Long ago, the local group formed as a collection of galaxies moving together through space, held by their mutual gravitational attraction. Over time, they have orbited their common center of mass, sometimes approaching, sometimes receding, but always bound together. Even now, the Milky Way, Andromeda, and the dozens of smaller galaxies in the local group remain gravitationally connected, their future evolution intertwined. Some galaxies orbit close together, others orbit at greater separations. This reminds us that galaxies are not isolated objects drifting alone, but members of gravitationally bound systems. Gas clouds can persist for millions of years. Long ago, molecular clouds formed from the accumulation of gas, swept up by spiral density waves and other processes. Over time, these clouds have drifted through the galaxy, sometimes passing through spiral arms multiple times, sometimes surviving in the quieter spaces between the arms. Even now, some clouds remain intact for 10 million years or more before finally collapsing to form stars or being dispersed by stellar feedback. Some clouds survive many passages through spiral arms. Others are disrupted more quickly, and the galaxy continues, turning, folding, moving through space and time. The galaxy's disk rotates in a single direction. Long ago, when the disk was forming from the collapse of a rotating cloud of gas, the material settled into a configuration where everything orbited the same way around the center, conserving the original angular momentum of the collapsing cloud. Over time, this directional rotation has persisted, with stars, gas clouds, and dust all moving in the same sense around the galactic center, creating the coherent spiral structure we observe today. Even now, nearly all objects in the thin disk continue to orbit in this same direction, a pattern established billions of years ago. Some stars in the disk orbit prograde, following the rotation. Others in the halo orbit retrograde, moving against the disk's rotation. This reminds us that the galaxy's different components formed through different processes, each with its own history, written in the orbital motions we observe. Stellar densities are highest near the galactic center. Long ago, when material fell inward during the galaxy's formation, it accumulated most densely in the inner regions, where gravity was strongest, creating the concentrated bulge and inner disk. Over time, this density gradient has remained, with stars crowding closer together in the central kiloparsecs than in the outer disk where the Sun resides. Even now, the stellar density near the center exceeds the density in our neighborhood by orders of magnitude, with stars separated by smaller distances, experiencing more frequent gravitational interactions. Some regions contain thousands of stars per cubic light year. Others, like the solar neighborhood, contain fewer than one star per cubic light year. This tells us that the galaxy's structure is highly centrally concentrated, with most of the stellar mass packed into a relatively small volume. The Milky Way continues to accrete gas from its surroundings. Long ago, the galaxy formed from the gravitational collapse of gas in the early universe, and this accretion process has never entirely stopped. Over time, fresh material has continued to fall into the galaxy from intergalactic space, feeding the disk with new hydrogen that sustains ongoing star formation. Even now, gas from the circumgalactic medium slowly spirals inward, replenishing what has been consumed by stars or ejected by supernovae and stellar winds. Some gas accretes directly from the intergalactic medium. Others come from recycled material that was previously ejected and is now falling back. This reminds us that galaxies are not closed systems, but continue to exchange matter with their surroundings over cosmic time. Gravitational microlensing reveals dark objects. Long ago, astronomers realized that massive objects, even if completely invisible, would bend the light from background stars as they pass between the star and Earth. Over time, surveys have monitored millions of stars, searching for these brief brightening events that signal the passage of an unseen mass across the line of sight. Even now, microlensing continues to reveal the presence of objects that emit no light, from rogue planets to stellar remnants to possibly dark matter clumps. Some lensing events reveal point-like objects. Others reveal extended structures with more complex signatures. This tells us that the galaxy contains many objects we cannot see directly, detectable only through their gravitational influence on light passing nearby. The galaxy's total luminosity comes mostly from stars. Long ago, when the first generation of stars began to shine, they provided nearly all the light emitted by the young galaxy. Over time, successive generations have continued this pattern, with stars dominating the galaxy's luminosity across most wavelengths. Even now, though gas clouds glow when illuminated by nearby stars and supernova remnants shine brightly in X-rays, the integrated light from hundreds of billions of stars produces far more total energy than all other sources combined. Some wavelengths show more emission from gas, others show primarily stellar light. This reminds us that despite the galaxy's complexity, with many different components and processes, stars remain the dominant source of electromagnetic radiation. Orbital velocities decrease with distance from the center. Long ago, astronomers expected that stars far from the galactic center would orbit more slowly than those closer in, following the same patterns seen in planetary systems where outer planets move more slowly than inner ones. Over time, observations revealed that the rotation curve remains surprisingly flat or even rises slightly at large distances rather than declining as expected from visible matter alone. Even now, this discrepancy between observed velocities and predictions from visible matter provides some of the strongest evidence for dark matter's existence throughout the galactic halo. Some stars orbit faster than visible matter predicts. Others orbit at speeds that require large amounts of invisible mass. This tells us that the galaxy's mass distribution extends far beyond the visible disk, dominated by dark matter in the outer regions. The Milky Way has formed stars for over 13 billion years. Long ago, in the galaxy's earliest epochs, the first generation of stars formed from pristine gas fresh from the Big Bang. Over time, star formation has continued without interruption, though at varying rates, creating stellar populations that span nearly the entire age of the universe. Even now, new stars continue to form in molecular clouds throughout the disk, adding to the hundreds of billions that already exist. Some epochs produced stars more rapidly than others. Others produced stars more slowly during quieter periods. This reminds us that the galaxy is not a static collection of stars all born at once, but a dynamic system where star formation has been ongoing for almost the entire history of the universe. Cosmic rays influence the chemistry of molecular clouds. Long ago, these high-energy particles, accelerated by supernova shock waves and other violent events, began streaming through the galaxy's interstellar medium. Over time, they have ionized atoms in molecular clouds, creating charged particles that drive chemical reactions even in the coldest, densest regions where ultraviolet starlight cannot penetrate. Even now, cosmic rays continue to shape the chemistry of star-forming regions, affecting the abundances of molecules that form on dust-grain surfaces. Some molecules form through cosmic ray-induced reactions. Others form through different pathways less dependent on ionization. This tells us that the energetic environment created by stellar deaths influences the conditions in which new stars and planets will eventually form. The galaxy's structure reflects its formation history. Long ago, the galaxy, assembled through the merger of smaller protogalactic fragments, each leaving an imprint on the final structure we see today. Over time, additional accretion events, interactions with satellite galaxies, and internal dynamical processes have continued to shape and reshape the galaxy's components. Even now, astronomers work to decipher this history by studying stellar populations, chemical abundances, and orbital motions that preserve clues about past events. Some features reflect ancient mergers billions of years old. Others reflect more recent interactions that occurred hundreds of millions of years ago. This reminds us that the galaxy's present appearance is the product of a long and complex history of formation and evolution. Some stars wander far from where they were born. Long ago, gravitational interactions with other stars, with giant molecular clouds, or with spiral density waves gave certain stars kicks that altered their orbits. Over time, these stars have migrated across the galaxy, moving radially inward or outward, sometimes traveling thousands of light years from their birthplaces. Even now, The sun itself may have migrated from a different radial position than where it formed, nudged gradually by encounters with massive structures over billions of years. Some stars migrate inward toward the galactic center. Others migrate outward toward the disk's edge. And through all of this, the galaxy drifts, quiet and vast, turning slowly through space. The Milky Way's mass is difficult to measure precisely. Long ago, astronomers began trying to weigh the galaxy by observing the motions of stars and gas clouds, using these velocities to infer the total gravitating mass. Over time, different methods have produced estimates that vary by factors of 2 or more, ranging from 500 billion to 3 trillion solar masses, with most current estimates settling around 1.5 trillion solar masses. Even now, significant uncertainties remain because most of the galaxy's mass comes from dark matter that cannot be observed directly, only inferred from its gravitational effects. Some measurements suggest lower masses. Others suggest higher masses. This reminds us that even fundamental properties of our home galaxy remain imperfectly known, still being refined as observations and methods improve. Radio observations penetrate obscuring dust. Long ago, visible light telescopes could only see a fraction of the galaxy, with vast regions hidden behind clouds of interstellar dust that scattered and absorbed optical wavelengths. Over time, radio telescopes revealed these hidden regions, detecting wavelengths that pass through dust relatively unimpeded. Even now, radio astronomy continues to map molecular clouds, trace magnetic fields, and reveal star-forming regions that remain invisible to optical instruments, providing complementary views that show cold gas where optical telescopes see only darkness. Some wavelengths are blocked by dust. Others pass through freely. This tells us that understanding the galaxy requires observing across the entire electromagnetic spectrum, piecing together a complete picture from many different perspectives. The galaxy evolves slowly over cosmic time. Long ago, billions of years in the past, the Milky Way looked different than it does today, with different star formation rates, different chemical compositions, different structures. Over time, changes have unfolded gradually, star formation declining from early peaks, the disk settling and thinning, the central bar forming and reshaping the inner regions. Even now, evolution continues, though on timescales so long that no individual human lifetime could witness significant changes. Some changes unfold over millions of years. Others require billions of years to become apparent. This reminds us that galaxies are not static objects frozen in time, but dynamic systems that age and evolve, though far more slowly than anything in human experience. Star clusters gradually lose members to the galactic tide. Long ago, when these clusters formed, they contained more stars, bound more tightly by their mutual gravity. Over time, gravitational interactions with passing molecular clouds, with spiral density waves, with the galaxy's overall tidal field, have stripped away their outer members. Even now, this slow dissolution continues, clusters evaporating star by star, their populations declining over billions of years, until eventually they will disperse completely into the general stellar population of the disk. Some clusters lose members quickly, others lose members more slowly. This tells us that even structures bound by gravity do not last forever, but gradually erode over the vast stretches of cosmic time. The Milky Way is transparent to neutrinos. Long ago, when the first stars began nuclear fusion in their cores, they produced not only light but also neutrinos, ghostly particles that barely interact with normal matter. Over time, trillions upon trillions of neutrinos have passed through the galaxy, through stars, through planets, through our bodies, almost as if matter did not exist. Even now, neutrinos from the Sun and from distant supernovae stream through the galaxy constantly, detectable only by enormous specialized instruments deep underground. Some particles interact with matter. Others, like neutrinos, pass through almost entirely unimpeded. This reminds us that the universe is filled with phenomena that remain invisible to ordinary observation, requiring extraordinary efforts to detect. Gas density is highest in the spiral arms. Long ago, when density waves began organizing the disk's structure, gas flowing into these regions experienced compression, increasing its density. Over time, this compressed gas has provided the raw material for star formation, creating the bright young stars that trace the spiral arms. Even now, molecular clouds accumulate preferentially in the arms, where densities reach levels sufficient to trigger gravitational collapse and ignite new stars. Some regions contain dense molecular clouds. Others contain more diffuse atomic hydrogen. This tells us that the galaxy's structure directly influences where and when stars form, concentrating star formation in particular regions rather than spreading it uniformly across the disk. The galaxy's future depends on dark energy. Long ago, before dark energy became the dominant force in the universe's expansion, gravity shaped the evolution of galaxies more directly. Over time, as the universe has expanded and accelerated, dark energy has begun to influence the future of structures like the Milky Way. Even now, the ultimate fate of the galaxy depends on how dark energy behaves over trillions of years to come. Whether the local group will remain bound while the rest of the universe recedes, or whether eventually even galaxies will be torn apart. Some futures involve eternal isolation. Others involve eventual dispersal. This reminds us that the galaxy's story extends far into the future, beyond the lifetimes of any stars currently shining. Stellar ages span from newborn to ancient. Long ago, the first stars formed when the galaxy was young, and some of their descendants still orbit in the halo today. Over time, generation after generation of stars have been born, lived, and in many cases died, creating a population that spans nearly the entire age of the universe. Even now, stars continue to form in molecular clouds, while ancient halo stars continue their patient orbits, a galaxy containing stars separated not just by space, but by time. Some stars formed billions of years ago, others formed only recently. This tells us that looking at different stars is also looking at different epochs in the galaxy's history, preserved in the stellar population. The Milky Way will continue to evolve for billions of years. Long ago, the galaxy began its long journey of formation and evolution, processes that continue today. Over time, slow changes will reshape the disk, alter the spiral structure, possibly merge with other galaxies. Even now, the galaxy's future stretches ahead through vast expanses of time, billions of years during which stars will be born and die, gas will be consumed and recycled, structures will form and dissolve. Some processes will speed up, others will slow down. And through all of this, the galaxy continues, turning slowly, quietly, patiently. Our galaxy is one of hundreds of billions in the observable universe. Long ago, when astronomers first realized that spiral nebulae were distant galaxies like our own, the universe suddenly became vastly larger. Over time, deeper observations have revealed more and more galaxies, each containing billions or hundreds of billions of stars. Even now, the Milky Way remains both unique, our home, and utterly typical. One ordinary spiral galaxy among countless others, all drifting through the expanding cosmos. Some galaxies are larger, others are smaller. The Milky Way turns on, soft and patient, through the quiet vastness of space, drifting, turning, endless.